Hello guys, and welcome to lab number 4. The title of this lab is the law of refraction. Before we go and start doing this experiment, we are going to do a quick review of the theory. We know that light has a dual nature. It can be considered a wave that propagates in the medium, and then also has a particle properties. We also know that light interacts with the medium through which it propagates. There's a whole line of different phenomena that we can observe that would explain or introduce the whole concept of light interaction with the medium, phenomena such as reflection, refraction, dispersion, etc. So one of those phenomena, so-called refraction of bending of light, is the topic of today's lab. We know that light propagates along the straight paths as long as it stays in the same medium. And when it passes from one medium into the other, it's going to change direction, it's going to bend, or it's going to refract. We also know that every medium can be characterized by its specific optical properties. The parameter that's very often used in practice is so-called index of refraction, that defines so-called optical density of the medium. The index of refraction would define a few important properties that go under the umbrella of interaction of light with the medium. Number one, index of refraction is going to define how much the speed of light is going to change. It's going to get reduced in a specific medium. And then also it is going to show how much is wavelength of light is changing. It's important to know that frequency of light is not changing when the light is propagating or passing from one medium into the other. And finally, index of refraction is also going to show us how much the light is going to bend or get refracted as it passes from one medium into the other. So as learning outcomes for this lab, obviously the topic is the law of refraction, so you should be able to state the law of refraction and know a little bit of theory behind it. You would be setting up an experiment, measuring certain and recording certain data, and then you're going to use that data to calculate the angle of refraction, and you're going to apply so-called Snells Law of refraction to quantify how much light bent as it propagated, as it passed from the air into the acrylic block. And then finally, you're also going to give some thought about common applications of the law of refraction, how we can take advantage of the law of refraction in practice. We are going to use the following equipment in this lab. Laser diode module. I'm using here an affordable red laser diode module. You can use any other class 1 laser or laser pointer. We are also going to use acrylic optical block to perform the measurements of the angles. We are going to use the protractor. We are also going to need a pencil and a white sheet of paper. To start this lab, first you're going to tape down the white sheet of paper, preferably 11 by 17 inch size. Once the white sheet of paper has been taped down onto your desk, you're also going to position the laser pointer parallel to the longer side of the paper, and then you're going to tape it down to hold it fast and steady at the location. After the laser pointer is positioned, the next step is to place the optical block. Before you position the optical block down onto the sheet of paper, you want to make sure that you inspect your optical block and make sure that it's free of any kind of dirt and fingerprints. It's also important to notice that it's not only the larger surfaces, these two large surfaces that need to be clean of any kind of dirt and fingerprints, but also these vertical edges, smaller surfaces, because that's where your laser pointer is going to be hitting and creating the effect of refraction. So if there's any kind of dirt or any kind of fingerprints on any surface of the optical block, you would want to clean it using proper optical component cleaning procedure. We are going to position optical block onto our white sheet of paper, and we are going to position it at a specific angle. What you can observe here, as we are rotating this optical block, we are going to have light ray coming out over on the other side, and as you're rotating this optical block, you can also observe how this beam over on the other side is changing, it's shifting. In order to successfully complete this lab, you want to make sure that the two sides of the optical block are used for the light to enter the optical block and exit the optical block are parallel to each other. So you can see that we are using this side of the optical block here to enable light to enter the optical block, and then the side that's parallel is the side where we're going to be getting the light out of the optical block. So you want to make sure that you're not using two adjacent sides of the optical block, but the two that are parallel to each other. Once you position the optical block, as shown here in this video, you're going to establish the footprint of your optical block using the pencil. To do that, you're going to hold the optical block steady, and you're going to mark 4 sides of the base of your optical block. And as a next step, you would want to mark the path of the laser beam. So in order to accomplish that, you're going to use the pencil. So you're going to move the pencil vertical to the path of the beam, and you're going to find a location at which beam hits the tip of the pencil. So here's the first dot that we are going to establish, and then we're going to move a little closer to the optical block and identify the next dot, and we can also establish one dot here closer to the aperture of the laser. So it's going to be right there. You're also going to do the same thing over on the other side where the light exits the optical block. So we are going to identify a few points. It's going to be the first point, the first dot, and then a few more dots along the way. Once the dots are marked for laser beam paths and the footprint of the optical block is established, we can remove the optical block and laser pointer to provide for more space for the rest of the experiment. Let's now improve our sketch. So first we are going to improve the footprint of our optical block. And the next step is to establish the paths of the two light rays, so incident and the refracted ones. So we are going to connect the dots for the incident light ray. So this is our incident light ray that's been produced by the laser pointer. Then over on the other side, we also connect the marking dots to establish the path of the refracted light ray. It's important to observe two events here. The first event is the refraction of or bending of the light at the front surface of the optical block that we are going to label with the letter A. And then over on the other side, where the light exits the optical block, we have a second event of a light refraction of light bending at the point B. So this is very important to observe. Very often very confusing to those who perform this experiment. So it's very important to understand that there's two events here, two light refraction events, one at the front surface and point A, and another one at the back surface or point B. We are going to connect points A and B. We know that light propagates along the straight paths as long as it's in the same medium, since we have acrylic block and we assume that it's a homogeneous material, meaning it has same properties all throughout the block. We can safely assume that the light is going to propagate from the point A to the point B along the straight line, so we can connect the points A and B to establish the path of the beam through the acrylic block. So as can be observed, we have incident light ray and we have bent or refracted light ray propagating through the acrylic block, and then at point B we have a second event of light refraction where light exits the acrylic and enters back into the air. In order to quantify the law of refraction, we are going to use so-called Snells Law of Refraction. In order to do that, we have to create so-called reference line or axis that is normal to the surface of refraction. So we have two surfaces of refraction here. the first surface is the surface where the point A is positioned. So at that point A, we want to create the reference axis that's going to be perpendicular to this front surface of the block. And then on the back surface where the point B is positioned, we can also create reference line here at the point B and quantify the Snell's law of refraction at that point as well. So let's start with the front surface. To establish the angle or the line that is perpendicular to the front surface, we are going to use the protractor. So in the protractor we have the origin at the protractor that we are going to position at point A, and then we also have this reference line at the protractor that we are going to use to align with the front surface. So again, the origin of the protractor is going to be positioned at point A. At point A, and then reference line on your protractor is also going to be positioned along the front surface of the optical block where the light refraction took place. And then we're going to go over here, look at a 90-degree angle that we are going to mark. And then we are going to connect our marking dot and our point A to establish the line of reference. So we're gonna use the dotted line to create that axis. We are also going to extend it into the block. So as we can observe here, the light that exited the laser pointer propagated along the straight line. And then at the point A, when the light moved from the air into the acrylic, we have an event of the first refraction where light changed direction, so it did not continue along the same path as the incident light ray, but started bending towards the axis, towards the reference axis. So in order to quantify how much the light bent or refracted, we are going to use the Snell's law of refraction. And in order to use the Snell's law of refraction, we have to measure the two distinct angles here. The first angle being so-called incident angle. That is the angle that the incident light ray makes with a reference line. We are going to label it here as theta 1. And then over on the other side, we have so-called refracted angle, angle theta 2, that refracted light ray is making with the reference line theta 2. We are going to measure these two angles using a protractor. So again, a quick review of how we can use the protractor. We have the point of origin at the protractor. We have this reference line. So this point of origin is going to go at the origin of our angle, which in our case is at point A. And then we are going to align the reference line on the protractor to our reference line on the sheet of paper. So right now the 0 is at the reference line, and we are going to count 10 degrees, 20, 30, 40, 41, 42, 43, 44. So our angle theta 1 is going to be equal to 44 degrees. Let's move over to the refracted angle. So again, positioning the protractor at point A and measuring the angle 10, 20, 29 degrees. So for the refracted angle we have 29 degrees, so our theta 2 is going to be 29 degrees. Let's now apply the Snell's law of refraction. The mathematical expression for the Snell's law of refraction is as follows: n1 times sine of theta 1 is equal to n2 times sine of theta 2. So this equation has a left-hand side and a right-hand side. Left-hand side represents all the properties of the first medium that light is entering from, into the second medium, which is on the right-hand side of this mathematical equation. So our N1 is an index of refraction of the first medium, which in our case is air. So we know that index of refraction of air is equal to 1. So now we are going to substitute N1 is equal to 1. Theta 1 is equal to 44 degrees, equal to N2 times sine of 29 degrees. We are going to perform these trigonometric operations. So 45 degrees sine is equal to 0.69 equal to N2 times sine of 29 degrees is equal to 0.485. And then from here we can calculate N2 measured equal to 0.695 over 0.485. Ends up being equal to 1.433. Now we also know what is the nominal value of the index of refraction of the acrylic. Nominal value of T2, of N2 is equal to 1.41. So we can calculate the percentage error for our measurement. So formula for the percentage error is right here. So you want to calculate the delta between, absolute delta between index of refraction that was measured and nominal index of refraction, and then renormalize to the nominal value of the index of refraction. And then of course you're going to multiply this by 100. So in our case the error percentage is going to be as follows: absolute value of 1.433 minus 1.41 over 1.41. So absolute value 1.433 minus 1.41 is going to be equal to 0.023 over 1.41, and then times 100. So we get for the percentage error, let's do the math, 0.023 over 1.41 is equal to 0.0163 or 1.63%. So the error of our measurement is about 1.63%, which is pretty good, taking into account pretty raw types of measurements and rounding that we performed during the trigonometric operations.